to this sheet titled Keep Colliding, bunch of fairly simple direct applications on collisions, but you know this will get you hands-on with collision. The first problem of the sheet is about this pulley system with a mass 3m at this end and a mass m here, right? And there is a particle of mass m and the whole system is at rest initially, let's say, and this mass m comes and strikes this mass m with a velocity u and gets embedded in it. Right? Now obviously when this gets embedded in it, the string gets strained a bit, instantly strained a bit, and if it gets strained a bit, that means there is tension, built up of tension in the string, there is an impulse associated with the string. Yes or no? Now, once this happens, what really transpires is that once this mass comes and hits this mass m develops a downward velocity v. This mass m, in fact the mass 2m, because m and m get embedded, and this mass 2m gets a velocity v downwards, and this mass 3m is party to the same velocity v upwards. Yes or no? Is party to the same velocity v upwards? Right? This is how it happens. So it's like this. This is what happens. Now, for sure, for the system comprising 2m and 3m, I can conserve linear momentum. First of all, I conserve linear momentum of this mass m, and this mass 3m, all put together. The tension, the impulse of the tension then is internalized, right? Because the impulse of the tension on 2m will cancel the impulse of tension on 3m, and they will produce together, they will produce no change in linear momentum on a system comprising 3m and 2m, right? So if you straighten it up, then the matters are like this. It's like as if this 3m has a velocity, I'm straightening this up, right? Has a velocity v to the right, and this 2m, so post collision, has a velocity v to the right, right? If I just straighten it up like this, then this is how the system will look, right? This is just after collision. And just before collision, the state is, there is 3m like this, there is, again straightening up just before collision, there is this u coming down, that means, you know, there is m into u like this. This is m, right? This is just before collision. I straighten up everything. This is how it looks. So what kind of linear momentum does this bring to the system? Mu? And it gets translated into this linear momentum, which is 3m plus 2m into v, which is 5mv. So the velocity, common velocity of 3m and 2m right after collision is going to be u by 5. How about it? It's going to be u by 5, right? Now, look at the mass 3m. Look at the mass 3m separately. The mass 3m. What acts on the mass 3m is an upward impulse j. Because of tension, right? And because of this impulse, it was originally at rest, now it develops a velocity v, right? So this impulse j of the tension must be 3mv, change in linear momentum of the mass, 3mv, which is like 3m into u by 5. That's the impulse of the tension. Right? Clear? Second problem of the sheet is about a particle of mass m originally at rest. And it undergoes a collision with some other mass, say m prime. Now during collision, the forces acting on the mass m vary like this, right? They peak out. This is how the forces between m and m prime vary with time as they collide. There is an impulse associated. Like I said before, the impulse will be area under the ft graph. The impulse acting on the mass is going to be the area under the ft graph, right? Isn't it? F dt is the impulse in a small time. The total impulse will be sum of this, where t runs from, let's say, t1 to t2, which is the area under the ft graph, which is the area under the ft graph, A. So the total impulse is going to be A, this area A, area, right? Total impulse is going to be A. And what does this impulse do to M? It causes the particle M to develop a velocity V. It was originally at rest. Now it develops a velocity V. What's the change in linear momentum of M? mv. So this A must be mv. So the velocity of the particle that was originally at rest now becomes A by m. Now becomes A by m. Yes or no? Clear? Third problem is about a ball moving normally to a wall. The wall is not stationary. God, it's dangerous if walls start to move. Think of this wall approaching you. Now that's a very dangerous thing to happen. But nevertheless, theoretically, everything can happen. So theoretically, this wall is moving with a velocity. And it's given that the ball undergoes a perfectly elastic collision with the wall. And I want to be able to find the velocity of the ball post-collision. Velocity of the ball post-collision is what I'm seeking. Now, here a reasonable assumption is the wall, obviously I will assume, is really massive compared to the ball, right? It's really massive compared to the ball, and therefore the post-collision, the velocity of the wall does not get affected. The velocity of the wall post-collision also remains. It does change by a little amount because there is transfer of momentum, but we will ignore that. That's a decent approximation if one of the masses is very heavy compared to the other one, right? So if I assume the same, then this is my wall. Post-collision continues to move with a velocity v, which is 5 meters per second. 5 meters per second. And the ball recoils with a speed vb. The ball recoils with a speed vb. This is what I'll assume, right? Now, very simple. This v naught is 20 meters per second. If I assume E is 1, then relative velocity of separation divided by relative velocity of approach. Now, if I take everything in this direction positive, right? And in the numerator I take ball minus wall, right? Ball minus wall. Then in the denominator I'll take wall minus ball, right? So I take ball minus wall, which is VB, which is what I seek to compute, minus 5, right? That's relative velocity of separation divided by relative velocity of approach. Now, in the denominator, I'll take wall minus ball. Now, this has a velocity in this direction itself, equal to, say, 5 meters per second. So, velocity of wall in this direction, which is 5 plus 5, because this direction is chosen to be positive, minus velocity of ball in this direction is minus 20. So, minus 20, which is VB minus 5 divided by 25. That's 1. So, VB then turns out to be 30 meters per second. Right? So this time there is a fixed obstacle here lying on a horizontal surface. And there is a string, and there is a particle at the end of the string. The string is fixed at O, and the length of the string is L. And the coefficient of restitution between the particle and the obstacle is given to be E. Now, the particle is taken to this position. And released. All right. It undergoes a collision. It acquires a velocity, say V naught. Right? If it undergoes a collision, then post-collision, what happens? The particle will have a velocity EV naught. because this is fixed. Yes or no? Right? Now, obviously, the particle has lost some kinetic energy. So it can't get back to its original position, right? It'll get, with this EV naught, see, if this was a perfectly elastic collision and if it had V naught, it'll get back to this position to conserve energy, right? But now if it has acquired a velocity V1, which is EV naught, which is very clearly less than V naught, then it will not deflect to that extent. It will deflect to this extent. Say after first collision, it will deflect to the extent of θ1, which is less than pi by 2, right? Now it falls back. It will hit the obstacle with a velocity V1 only. V1 only, right? Because between this swing, there is no loss of energy. So if it has just come back, then just before collision, it will have a velocity V1. And then post collision, it will have a velocity V2, which is EV1. And then it will deflect. It will deflect by an amount θ2, which will still be less than θ1. It will then come back and hit with a velocity V2 and would rebound with a velocity EV2. It will deflect by θ3 and so on and so forth. Now what's required in the problem is the deflection after n collisions, the angular deflection θ after n collisions. This is what is required. You know what I'm saying? This is what is required. Now, so after first collision, what is the velocity? EV naught. After first collision, right? After second collision, what is the velocity? See, it will come back and hit with a velocity EV naught, so it will rebound with a velocity E times EV naught. So E squared V naught after the second collision. After the third collision, so now it goes with the velocity E squared V naught, it will deflect by a certain angle, it will come back and hit with the velocity E squared V naught, but it will reflect, rebound with a velocity E times S, that means E cube V naught, and so on and so forth, right? And after the nth collision, it will rebound with a velocity E to the power n V naught is the velocity with which it will rebound, right? This is what would happen. A particle of mass m. Now, what is V naught? V naught is the kinetic energy obtained when it falls by an amount L, right? It starts from rest, it falls by an amount L, the radius of the string, so loss of potential energy is mgl, and where does it go? It translates as kinetic energy half mv naught squared. V naught is the velocity with which it first hits the obstacle. So very clearly V naught would be root 2 gl. V naught would be root 2 gl. So now we have this velocity after the nth collision, which is Vn, which is e power n V naught. V naught we know is root 2 gl. Now what happens? This is O, this length is L, this is the velocity subsequent to nth collision, and the string deflects by an angle θn. After nth collision, it deflects by an angle θn, right? Now if it deflects by an angle θn, do you realize what's the kinetic energy that the particle has at this point when it rebounds? Half m Vn squared. And that must be gain of potential energy, mg into gain of this height. Now what is this height? This is L. This is L. So this is L cos θn. So gain of height is going to be this. This would be my gain of height, which would be L minus L cos θn. So L into 1 minus cos θn is the gain in height, right? So this must be mg into L into 1 minus cos θn. And Vn squared, as you can see, so this is half m. Vn squared is e to power 2n into V naught squared, right? E to power 2n into V naught squared. That must be mgl. What is 1 minus cos θn? 2 sine square theta n by 2. 2 sine square theta n by 2. 2. So this 2 can come down here. fourth m and m will get cancelled, and v naught squared is 2gl. So then we have half of e power 2n gl is gl into sine square theta n by 2. I hope all of you realize whatever I've done. V naught squared is 2gl. We'll make this. GL will get cancelled, and then we have sine theta n by 2 is e power n by root 2. E power n by root 2 is what you get. So if sine theta n is known, you know theta n. Sine theta n by 2 is known. So theta n by 2 would be sine inverse this. Theta n is going to be twice sine inverse e power n by root 2. Yes or no? Straightforward problem. There is a particle of mass m moving with a velocity v naught, undergoes a head-on collision with an identical particle of mass m at rest, and the coefficient of restitution is half. We want to find the impulse acting on each of the particles. Well, impulse acting on any particle will be change in linear momentum of the particle, right? Would be change in linear momentum of the particle. That means, and very clearly, total linear momentum is constant, right? So change in linear momentum of one particle will be negative of the change in linear momentum of the other particle, so that there is no net change in linear momentum of the system. So it's enough, if you want to compute the magnitude of the impulse, it's enough to compute the magnitude of the change in linear momentum of any one particle, right? So let's do that. V1 and V2 are velocities post collision. Before collision, this is V naught, this is at rest. So let me first conserve linear momentum of the system. So mv naught is the total linear momentum that this comes with, and it shares it with the two particles, so which is m v1 plus m v2, right? And then coefficient of restitution, E, which is half, which is relative velocity of separation divided by relative velocity of approach. So if in the numerator I take v2 minus v1, then in the denominator I'll take v naught minus 0. Yes or no? So that gives me v2 minus v1 as half v naught, right? And this m and m will get cancelled. v1 plus v2 is v naught. Yes or no? So I can calculate, let's say it'll suffice if I just calculate v1, for example, or just v2, either way, right? So let's say if I calculate v2, because just when I add these two I can readily calculate v2. 2v2 is 3 by 2 v naught when I add these two. So v2 is 3 by 4 v naught. And what's the change in linear momentum of this? mv2 is the change in linear momentum of this, and that must be the impulse acting on this. That must be the impulse acting on this, which must be equal in magnitude to the impulse acting on this. That will be the same as the magnitude of the impulse, m v1 minus v naught. Same aana chahiye, right? So this is m into v2, which is 3 by 4 v naught. So 3/4 mv naught is the impulse acting. Magnitude of the impulse acting on each particle is this. However, they would be in opposite directions, right? So there are these two particles, masses m1 and m2, headed towards each other with these velocities, 5 meters per second and 10 meters per second. And the coefficient of restitution is 0.5. That means, it's not a perfectly elastic collision. There is loss of kinetic energy, right? We need to find the loss of kinetic energy. Now, I have given you a result for that. In my last class, the loss of kinetic energy is of the magnitude. Now, this, of course, I want you to remember, is half mu into initial velocity, relative velocity squared into 1 minus e squared is a result that I might have told you in my last case. Where what is mu? Mu is the reduced mass. Mu is m1 m2 by m1 plus m2, which you can compute. So 18 by 9, which is 2 kilograms, is the reduced mass. E obviously is given. And what is urel? Urel is 5 meters per second. Relative velocity is 5 meters per second. Whether you take this minus this or this minus this, when you square it, it'll be even Stevens. So you know everything. Mu, urel, E, and you would get the change in kinetic energy, total change in kinetic energy associated with such a collision. You don't have to find V1 and V2. You can directly use this result, right? Half mu V initial relative velocity squared into 1 minus e squared. Very clearly, if E is 1, that's a perfectly elastic collision. There is no change in kinetic energy. Kinetic energy in that collision will be preserved. Right? And when E is 0, there is maximum loss of kinetic energy. Because when E is minimum, this quantity would be maximum. E's minimum is 0, which is a perfectly inelastic collision. Then the change in kinetic energy would be greatest. Right? The problem, however, says they're moving towards each other 10 meters per second. Then obviously relative velocity would be 15 meters per second. That's a correction that you want to make. Relative velocity would be 15 meters per second if they're moving towards each other. Right? So the next problem is about two disks. A smaller disk of radius small r, mass small m, a larger disk, mass capital M and radius capital R. And this disk is initially at rest. That's given in the problem. And this disk has a velocity v0 as shown. This is the line of traversal of this disk. This is the line of traversal of this disk. And the two centers are vertically separated by a distance d. That's given in the problem. So this is the state before collision. I want to figure out what would be the velocities of the two disks post collision. This is what we want to figure out. So see, what really happens is when they just collide, see, this is the bigger mass, this is the smaller mass, right? The velocity of this is v0. This is the line joining the two centers. O, let me call it an O prime. O and O prime. This is the line joining the two centers, which will also be the common normal, which would be the line of impact. Collision is felt only here, right? This is radius capital R. This is radius small r. So is it head-on collision or oblique collision? Oblique collision, because realize the velocity of any one particle, if it's not along the line of impact, then the collision is an oblique collision. Oblique collision, right? It's given that the collision is perfectly elastic, and we'll assume, if nothing is given, we'll assume that all surfaces involved in collision and the ground, they are all smooth. We'll assume. Now, this is initially at rest. It's initially at rest. This velocity could be resolved along the line of impact and perpendicular to the line of impact. So this is like v0 sine theta this way and v0 cos theta like this. v0 cos theta like this, right? Now, this velocity component would have changed only if there was friction, right? See, this is tangential component. It's perpendicular to the line of impact. So this is only subject to change if there is friction between the colliding entities. But we'll assume that there is no friction between the colliding entities. So post collision, so this is JBC, just before collision. Just after collision, our fellow here, this component of the velocity, it retains. v0 sine theta, it retains. But in this direction there is collision, in this direction there is collision. So its velocity does not remain v0 cos theta in this direction. Along the line joining the two, the velocity of this becomes v1. Now again, for the mass capital M, this is the tangential direction perpendicular to the line joining the two centers. It had no velocity before collision in this direction. It had no velocity before collision. So obviously, because there is no friction, it will not develop any velocity in this direction post collision either, in the tangential direction, right? A direction perpendicular to the line of impact is the tangential direction. Velocities in that direction will get remedied or changed only if there is friction, but no friction. So it doesn't. That means the only direction in which its velocity would build up is this. So this is, let's say, post collision, it develops a velocity v2. This is mass capital M. Now, what are the two things you'll do? One, you will conserve linear momentum along this direction, right? Although you can conserve linear momentum in any direction, but it's not required to conserve linear momentum in other directions. So in this direction, what do we have? along the line of impact, mv naught cos theta is the total linear momentum before collision along the line joining the centers, and post collision, that's like a capital M v1, I'm sorry, small m, and this is capital M, small m v1 plus capital M v2, right? Post collision. And then I would have to use the fact that the collision is perfectly elastic. For that, what am I going to do? E is 1. E is 1. So what's E? Relative velocity of separation along the common normal. So I'll take v2 minus v1, let's say, in the numerator. v1 and v2 are two unknowns to me, right? v2 minus v1 divided by velocity of approach, v naught cos theta minus 0. Minus 0, and that must be equal to 1 because the collision is perfectly elastic. So that gives me v2 minus v1 as v naught cos theta, equation 2. So this is conservation of linear momentum, and that's perfectly elastic. So two unknowns, v1 and v2, two equations. I can solve for v1 and v2, and I would know the velocities of the two particles along the line of impact, right? This equation, this equations, two unknowns, and we can obtain v1 and v2 from these. Clear? So the next problem, there are two particles, one of mass m, the other one of mass 2m, at the same horizontal level. One chucked with a velocity 10 meters per second to the right, the other one chucked with a velocity 5 meters per second to the left. They collide in midair and the combined mass falls somewhere. We want to find how far from A the combined mass is due to fall. Right? Now, one thing, when they're launched, see, horizontally there is no external force acting on the system. Yes or no? So linear momentum of the system will be conserved in the horizontal direction. Yes or no? Because there are only vertical gravitational forces acting on the system, no horizontal forces. So linear momentum in the horizontal direction will be conserved. Now, what's the linear momentum initially? Hey, m into 10 minus 2m into 5 is the linear momentum initially in the x direction, which is 0. Yes or no? Right? That must be at any point of time total mass of the system into velocity of the center of mass in the x direction. Linear momentum in the x direction is mass into velocity of center of mass in the x direction initially. So velocity of the center of mass in the x direction is 0 initially and will remain 0 all the time. Why? Because linear momentum will be 0 at all instants in the x direction for the combination, right? That means if the center of mass is, even though this particle is drifting to the right, this particle is drifting to the left, the x coordinate of the center of mass will not drift. Why? Because in the x direction the center of mass has no velocity. In the x direction the center of mass has no velocity. So the center of mass will maintain its x coordinate. The center of mass will maintain its x coordinate. Yes or no? So which means, what's the x coordinate of the center of mass initially? That's going to be the x coordinate of the center of mass all the time. Okay, let me call this position x equal to 0. All points here is x equal to 0. All points here are x equal to 60. Right? So initial x coordinate of the center of mass, I am calling this as my x direction, is going to be what? M into 0 plus 2m into 60 divided by 3m, which is 40 meters. 40 meters. Yes or no? That means eventually when they fall as a combined mass, they will fall somewhere here at a point D, which is 40 meters from A. See, when they undergo a collision here, this has a velocity 10 meters per second and this has a velocity 5 meters per second, right? And their net linear momentum horizontally will be 0. So the combined mass will have no velocity in the horizontal direction. The combined mass will fall vertically down. And it will fall at a distance 40 meters from A. It will fall at a distance 40, because that's going to be the x coordinate of the center of mass at all times. Why the x coordinate of the center of mass is not changing? Because the velocity of the center of mass in the x direction is not changing. That's why. Got me? So here we have two identical masses P and Q undergoing a collision. This was initially at rest, and this has a velocity 10 meters per second, making an angle 30 degrees along the line of impact. This belongs to collision. Line joining their centers will belong to collision. We want to figure out what happens post collision, right? We'll assume again, all particles are smooth, right? Now this velocity could be resolved as 10 sine 30 degrees means 5 meters per second in the tangential direction, and 5 root 3, 10 cos 30 degrees is 5 root 3 meters per second along the line joining the centers, right? And this has a zero velocity along the line. Zero velocity in this direction, its velocity is also 0 meters per second. Do you realize the velocities in the tangential direction will be preserved? So this will continue to have a velocity 5 meters per second in this direction, 0 meters per second in this direction. Why? Because there is no friction. So in the tangential direction, there would be no alteration of their velocities. Why? Because particles involved are smooth. And along the line joining the two centers, they are identical particles in a state of perfectly elastic collision. What will happen to the velocities? They will exchange their velocities. Along the line joining the centers, the velocity of this will become 0 in this direction, but will remain 5 meters per second in this direction. The velocity of this now will become 5 root 3 meters per second in this direction, and will remain 0 in this direction because this is what would happen. That means this particle is moving like this, and this particle is moving like this. That means they are moving perpendicular to each other. They are moving perpendicular to each other post collision, right? Right. So, the next problem is about this stationary wedge. ABC is a stationary wedge whose mass is known to us, 0.05 kilograms, right? And there is a particle of mass 0.01 kgs. It's moving horizontally. It's moving horizontally with a velocity of 20 meters per second and hits the wedge at A and comes to rest. After collision, this hits the wedge and comes to rest. That means it transfers its entire linear momentum to the wedge, right? So post collision, this comes to rest, whereas the wedge starts to move with a velocity Vw. The wedge starts to move with a velocity Vw, right? So, can I find the velocity of the wedge post collision? Yes, I can conserve linear momentum. M into U must be mass of the wedge into Vw. Mass of the wedge is 5 times the mass, so velocity will become 1/5. So Vw would become 4 meters per second. Yes or no? This is what happens to the wedge post collision. This is the story of the wedge post collision. Now, what happens to this particle? They say the particle comes to rest. Now, if this particle, so can I remove this data from the top? So if this particle comes to rest post collision at A, right? This particle of mass small m comes to rest. So what would happen to the particle? The particle will fall vertically down. The particle will fall vertically down. Whereas the wedge will move rightwards. Now, the particle takes a certain time to reach D. The particle takes a certain time to reach D. Hey, do you realize I need to calculate the length AB, by the way? So let me write everything in terms of AB, right? AD is AB cosec AB sine theta. AD is AB sine theta. This is AB sine theta. So the time taken by the particle to fall to the ground, would be root 2h by g. 2 times the height through which it falls, 2 times AB sine theta by g. Now sine theta I know because cot theta is given to be 2, so I know the value of sine theta. Sine theta would be 1 by root 5. Sine theta would be 1 by root 5. Cos theta would be 2 by root 5. Right? So that's the time taken by the particle to fall through this vertical height. Now, if wedge were to be stationary, the particle would have hit the point D. But the wedge has translated to the right. So in the time, and they say that the particle hits the wedge, the second collision of the particle with the wedge occurs at this vertex B. Which means by the time the particle falls through height h, the wedge would have moved this distance. B would have come to this point. B would have come to this point. Yes or no? And what's the time taken by B to come to this point? Time taken by B to come to this point would be this distance BD, which is AB cos theta, right? AB cos theta divided by the velocity of the wedge, which is 4 meters per second. In a time in which the particle falls through this height, the wedge translates the distance BD so that the particle, instead of hitting D, it will hit B. Yes or no? Now, I know sine theta. Sine theta, as you can see, is 1 by root 5. Cos theta is 2 by root 5. I can plug in the value of sine theta, cos theta and solve for AB. Solve for AB. Isn't it? Clear now? And they say at the instant of collision, what's the normal reaction from the ground? Normal reaction from the ground would be weight of the wedge, mg. Normal reaction from the ground will only be weight of the wedge, mg. Because this particle, when it hits this, has no vertical impulse that it gives to the wedge. It's moving horizontally. So the normal reaction from the ground is going to be mg, the weight of the wedge. Right? So the next problem, again, fairly simple problem if you evaluate it. There are two identical blocks, A and B, resting on top of each other, right? Identical masses, capital M. There is a particle like bullet that's moving horizontally, hits the lower block and gets embedded in it. The lower block will therefore develop a velocity. The lower block will therefore develop a velocity. In order that B could be, A and B could move together, there is development of friction between A and B. There is rubbing between the two. There is relative motion for a while. There is relative motion between A and B for a while. After which relative motion stops. Because friction, the idea of friction is to eventually put an end to relative motion. Right? Yes or no? Yes or no? So, after relative motion has stopped, what would have happened? What would have happened is, both the blocks after could be looked upon, along with the bullet, could be looked upon as a single mass, 2m plus mass of the bullet having a final velocity Vc, After rubbing has stopped, every entity here would have a common velocity Vc, yes or no? Right? Now, can I find Vc? How? Conservation of linear momentum. And how can I conserve linear momentum? There is friction between the two. Yes, for the system I can. I can't conserve linear momentum of B. I can't conserve linear momentum of A, but I can conserve linear momentum of A and B. Why? Because between A and B, friction is an internal force. It does not participate in changing the linear momentum of the system. Friction will change the linear momentum of A, it will change the linear momentum of B, but not of A plus B. Right? So I can find the final common velocity of that single lumped mass. Right? How? 2m plus small m into Vc. That must be equal to m into V. So Vc then is mv by 2m plus small m. Now, do you realize there is change in kinetic energy? Work done by all forces put together would be change in kinetic energy. N and mg are not doing any work, so it must be friction which is doing work. So change in kinetic energy must have been work done by friction, right? So work done by friction must have been change of kinetic energy, which is half of 2m plus small m into Vc squared minus half of small m into V squared. That must have been the work done by friction. That must have been the work done by friction. Change in kinetic energy. Right? So now the next problem is as follows. There is a particle of mass small m launched up with a velocity v naught, right? It come back, I'm showing it at different stages, but it happens along the same vertical line. Only symbolically I'm showing as if it's happening at different points. It goes up, it comes back, it hits the ground with a velocity v naught and rebounds with a velocity v1, right? Now it goes up, it falls back, it hits the ground with a velocity v1 but rebounds with a velocity v2. Comes down, hits with a velocity v2, rebounds with a velocity v3. This will happen infinity of times. This will happen infinity of times. We need to find the total impulse exchanged between the ground and the earth, ground and the particle. This is what so first of all, you know, v1 you realize would be E times v naught, right? v1 would be E times v naught. v2 is going to be E times v1, right? Which is like E squared times v naught. v3 is going to be E cube times v naught, and so on and so forth. This you understand, right? Now, look at the first collision. What is the change in linear momentum here? What is the change in linear momentum? First of all, do I look at this also, change in linear momentum here? Particle is changing linear momentum. So I look at change in linear momentum here, mv naught. What's the change in linear momentum of the particle here? M v1 plus v naught. What's the change in linear momentum here? M into v2 plus v1. M into v3 plus v2. Yes or no? That's a total change in linear momentum? Yes or no? That's a total change in linear momentum of the particle up to infinity, right? This is like m into, realistically, you know, I can ignore this quantity because somebody is launching it up. So I can ignore this quantity. So it's only during impact that I would take change in linear momentum as the linear momentum or impulse transmitted or exchanged by the particle and the earth. So this, let's say somebody is launching and is moving out of the sea. So let me start with this only, realistically. So this is like m into v naught plus v1 will occur twice, v2 occurs twice, v3 occurs twice, up to infinity, right? This is m into v naught plus twice, v1 is E times v naught plus E squared times v naught plus E cube times v naught plus, right? This is m v naught into 1 plus 2e by 1 minus e. Realize infinite GP series, e plus e squared up to infinity, e by 1 minus e, which is mv naught into 1 plus e divided by 1 minus e. That's the total impulse exchange between the earth and the particle. Clear? This one problem involves a wedge of mass capital M initially at rest. And there is a particle that impacts the wedge normally with a velocity v naught, right? And the coefficient of restitution between the wedge and the particle is given to be E. E is obtained about events happening along the common normal, that means along this. And all involved surfaces are smooth. All involved surfaces are smooth. I need to find v1 by v naught, velocity of the particle post impact divided by the velocity pre impact. This is what v1 by v naught is my agenda here, right? Now, first things first. So, horizontally, say this is the normal. Normal will make an angle alpha with the vertical if alpha is the inclined plane, right? Right? Now in this direction, horizontal direction, can I conserve linear momentum? Yes. Horizontally I can conserve linear momentum. What's the linear momentum that the particle brings to the system? mv naught sine alpha. Yes or no? This is v naught sine alpha. Do you realize this? V naught sine alpha. mv naught sine alpha. That must be equal to the final linear momentum horizontally. Now that's capital M into V2, and the particle rebounds like this. Post impact, right? So V1 has a horizontal, so V1 is the velocity perpendicular to the plane after impact. So V1 sine alpha horizontally and V1 cos alpha vertically. So then, so mv2 minus mv1 sine alpha. 1. Equation 1. And then next, what am I going to do? Coefficient of restitution, right? Coefficient of restitution. This is V2. This angle is alpha, etc. Relative velocity of separation along the common normal divided by relative velocity of approach along the common normal, right? Separation, I look at this. And this is the common normal. Along the common normal, the velocity of the particle is V1 like this. The velocity of the wedge is V2 rightwards, but along the common normal, it's V2 sine alpha. Yes or no? So E must be what? V2 sine alpha minus V1, right? Minus V1, right? I have taken wedge minus particle in the numerator, so in the denominator I must take particle minus wedge. So particle is going to be V naught and wedge is 0 initially, right? So V naught along the common normal minus 0. So that gives me like EV naught is V2 sine alpha plus V1. That's my second equation. I want to be able to find the value of V1 by V naught. What you can do is you can divide throughout by V naught. So this will be one variable V2 by V naught. This will be another variable V1 by V naught. This also you can divide by V naught and you will get E equal to V2 by V naught sine alpha plus V1 by V naught. Right? So two unknowns, V1 by V naught and V2 by V naught, and you can solve for V1 by V naught from these two equations. Right? Now there is a ring of mass capital M lying on a horizontal surface, smooth horizontal surface, right? And these are two beads. These are two beads that are clutched onto the ring, each of mass M. You know, so a bead can essentially slide along the ring. This is a bead. You know what a bead is. It can slide along the ring, right? And there is a bead of mass small m here, and there is a bead of mass small m there, right? And they are imparted tangential velocities, identical tangential velocities v and v. Eventually, realize that this bead would move like this along the circumference, this bead would move along the circumference, right? Now as they move along the circumference, do you realize that so one thing, while these beads move, say after a while, because of symmetry, the beads would be, let's say, this bead would be here at an angle theta after a while, this bead would be here at an angle theta after a while, right? This bead would have had a velocity, let's say, v prime like this. This bead would have had a velocity v prime like this. Because of symmetry, there is no distinction between the two beads. And if this was my x-axis, then what was my total initial linear momentum in the system? 0 along the x-axis, but not in this direction. In this direction, linear momentum is 2mv. Linear momentum is 2mv. Yes or no? But in this direction, linear momentum is 0. Consequently, you know, this component of velocity of this in this direction and component of velocity in this direction, their linear momentum in this direction will cancel each other and will maintain 0 linear momentum horizontally of that system, right? And this, so the horizontal linear momenta, because of symmetry, is taken care of by the two beads itself. So the ring is removed from the horizontal direction in the sense that it doesn't have to participate in linear momenta transfer horizontally. The ring therefore does not develop any horizontal velocities because it didn't have to, because their linear momenta in the horizontal direction itself cancel off, and the ring did not have to produce linear momenta to cancel off horizontal linear momenta. So the ring will over a period of time move downwards. Again, why would it want to move downwards? Because realize that in the vertical direction there is change in linear momenta of the particles, but in the vertical direction the linear momenta would have to be conserved. This particle would push the bead down, would push the ring downwards. This particle, as it's moving tangentially, would push the ring downwards. So the ring would develop a downward velocity. The ring would develop a downward velocity, but even in this direction, at all times, the linear momentum of this particle downward plus linear momentum of this particle downwards plus the linear momentum of the ring downwards will at all times be 2 mv. And in the horizontal direction, the linear momentum would be 0 at all times, guaranteed, right? Again, where do you expect the two to collide? From symmetry, again, the two would collide at this point P, vertically downwards, right? Now, so after a while, the ring would have descended down. The ring would have descended down. The ring, mass capital M, would have developed a velocity v0, right? The two particles, M and N, when they collide, they would have tangential velocities only, which will cancel each other. They would have tangential velocities which would cancel each other. Plus, do you also realize they would also have a velocity v0? They will have tangential velocities whose linear momenta would cancel each other, and they would have a velocity in this direction same as that of the ring. Yes or no? That's a condition to maintain contact, isn't it? Do you realize that? Good. Which means, does this give us an opportunity to compute v0? Conservation of linear momentum in this direction would enable computation of v0. Yes or no? So what's the total linear momentum that we started with in this direction? 2 mv. And that must be capital M plus 2m into v0. Capital M plus 2m into v0 in the vertical direction. So I know v0. v0 is 2mv by capital M plus 2m. What's the kinetic energy of the ring? Kinetic energy of the ring is going to be half of capital M into v0 squared. v0 has been computed. As simple as this, right?